If you want to send out a signal from one computer to all the other computers, how long is that going to take to reach every single other computer? Hi everybody, and welcome to another mock interview with Exponent. Today we're here with Daniel for a software engineering question. Daniel, would you like to introduce yourself?
Yeah, hi. My name's Daniel. I'm a former engineer at Coinbase and Intuit, and yeah, looking forward to it.
Great. Thanks so much for being with us today. All right, let's get started. So the question for you is, if you have a network of computers and they all connect to each other at different speeds, for example, you and I and a third person named Anne are on the same network, and you can connect to me in 2 seconds, I can connect to Anne in 4 seconds. If you want to send out a signal from one computer to all the other computers, how long is that going to take to reach every single other computer?
So I think I'll start out just by drawing out that example that you gave.
Mhm.
So I have a little computer icon here. So this was me, and then we have you over here, and down here we have Anne, and I think it was, I can't remember, but I'll just make up some numbers.
Sure.
It's 6, and so it takes 6 seconds to get from my computer to your computer, and 2 seconds to get from mine to Anne's computer. So I'm just gonna kind of think through this scenario first. So let's say we start this message at my computer. We go to your computer. That takes 6 seconds. We go to Anne's. That takes 2. So it would take 6 seconds to get to all the computers in this
Mhm.
system. So that's a pretty easy example. And just like the first thing I see is that we're just following these lines from, let's say, the starting position is my computer. So maybe we have another computer here. So what would happen if, let's say, what would happen if Jill, for example, doesn't have a connection to anyone else? If there's no way to get to her computer, what would we
So if you,
want to return?
let's say you return a -1.
Okay, all right, we can return -1 in that case. So in this case, we would probably need to know not just the connections, but we would probably need to know all the computers, the whole number of computers in the system, just in case we couldn't connect to one of them.
Mhm.
So let's do a little bit more complicated example. So right here, we can get from me to you in 6. But let's just say, for example, we go down here. Let's say we can get to Jill in 2. And we can get to you from Jill and another 2. So I'm just going to make a little circle that represents our, let's say this is our information packet or something.
Mhm.
So this one starts out, it hasn't taken any time yet. So let's say it's 0. And then let's say it goes down to Anne, and this takes 2 seconds. And then it goes to Jill. This also takes 2 seconds. And then it goes to you. This takes 6 seconds. So we've only gone out from the source computer, and it would look like the longest it would take is 6 seconds. But if we like look a little bit closer, we can see that this one actually makes a shorter path to you through Jill here. So let's try like propagating this signal. If it goes along this path, it took 2 seconds to get here. It's another 2 seconds. So that's going to be like 4 seconds.
Mhm.
So we kind of have two messages that reached you from different paths. So this is kind of interesting. And then, yeah, let's say we have another one. And we have this 2 here. And this message, we can try doing the same thing we did up with Jill, like propagating this message up here. And this is going to be 3. And then I'm like thinking if we propagate this 3 up to here, this 5. But if we look at this 5, we kind of look at the numbers here, and we actually don't really care. It seems like we don't really care about the 6 and the 5, because once it reaches 4 seconds, it's already gotten to you.
Mhm.
We really only care about what what the fastest it can get to each computer, basically.
Yes.
So I'm trying to think of some way that we can like get rid of these, basically. And this 5 is coming from this 3. And we can kind of see it's following the same path as this 2. So both of these, this 4 and the 5, come from Jill.
Mhm.
But we already know here, once it reaches Jill, we already know that this 2 is always going to be faster. So I don't think we really would need to propagate this 3 over here. So we probably won't even need to do that. So that's one case that we can think of as not propagating those.
So you're dropping anything that's slower than another baseline.
Yeah, exactly. Like if it reaches a computer and we have already gotten a message that's faster, then
Mhm.
maybe we don't send that new message out again from that computer. And this is I'm just kind of like playing around with ideas here, but
Yeah.
So yeah, that seems like some good examples to think of.
Mhm.
So what is like the format that we get this question in? Like what does like our input look like?
So let's say you get a list of lists. Each index in that list corresponds to an edge in this network, and the element of that index is a list of 3 things, 3 numbers. The first one is your source node, the second one is your destination node, and the third is the value of the speed along between those 2 computers, those 2 nodes.
Okay, so let's do that. I'm gonna write out just like for this example what this would look like. So and say these are like the edges, and then I'm actually gonna rename because you said that these are all supposed to be indexed. I'm just going to take away the names and kind of like abstract this to be these to be labeled as numbers.
Okay.
Okay, so from computer number 1, we go to computer number 2, and that takes 2 seconds. From computer number 1 to 3, that's also 2 seconds. 1, 2, 4, that's also 2 seconds. And then we have 2 to 3 in 1 second. 3 to 4 in 2 seconds. And I think that's all of them. 1, 2, 3, 4, 5. Yeah. So yeah, now that we like kind of played around with this a little bit, I want to think of kind of how I want to represent this in code. So our
Can
input is a
I,
list.
sorry, can I just confirm how you're getting from 1 to 4?
So from 1 to, there's a couple paths from 1 to 4. Like we have this 6 right here, which is, oh, I see what you're saying. You got the wrong one up here. From 1 to 4 is 6. Is that where you're getting at?
Yeah.
Okay, cool. Yeah. So, yeah, so how do we want to represent this? So we have a list as input. So we could do something with a list, but like just from drawing it out, this looks a lot like a graph problem. We have computers, which could be nodes. We have these edges. We've already called them edges. They're like kind of like weighted edges. And we also want to, we're kind of traversing this graph, sorry, basically. And now I want to figure out what these numbers represent in the graph. So we have a couple of numbers and we know they represent like this 2 and the 3 here. We know that they represent the length from different paths. But like we said before, we don't really care about the bigger ones because we only care about the fastest time that it takes to access. So if we just get rid of these, thinking these, basically what these represent is the shortest path from our source to this specific vertex, this specific computer. So yeah, all that combined, this makes me think this is like a pretty good candidate for a graph problem and probably like a shortest path problem.
Okay. Sounds good.
Yeah. So I'm just gonna start by I'm gonna write out some pseudocode just to see basically like what we did before. I'm gonna copy this and kind of go down a little bit. We'll go down here. So there definitely are some like shortest path problems that we could take off of, but I'm just gonna like continue to do this kind of based on intuition, and then maybe we'll like discuss the optimizations and like the specific algorithms after that.
Sure, that sounds good.
Okay. All right, so the first thing is like we want to have this message that is supposed to be propagating. So we know that we start with source node and takes 0 seconds to get there. And then our second step was propagating this to these other computers, which are really like the children of this node. So we have this message and we want to propagate the message to the children. And we also want to take into account like how long it took to get there. So say this message took 2, this one's also 2, and this one's 6. So we want to propagate the message to the children and how long the message. And then, like we saw before with this case, we need to make sure that at least for these ones, we continue to propagate the message, because there could be some paths down the line that actually get shorter based on like some undiscovered paths. So like here, we want to propagate the message. So this almost seems kind of recursive. So maybe that's something we could think about. Like we basically want to do the same thing at this node as we did with the first node. So I'll keep that in the back of my mind. And so we want to continue propagating messages until, or let's say continue propagating messages if. So I'm trying to think of cases where we would not want to continue with the message. So like for this case, we have this 6 here, and this node doesn't have any children. The 4 node doesn't have any children. So that's already where we're gonna like not be able to propagate there. So we'll say if it has children, we can propagate. But then the other case when we came back here was where we have a message that actually takes longer to get to the computer than a message that has already gotten there. So, and we kind of saw earlier that it's kind of pointless to propagate this message because wherever this 3 gets propagated to later, the 2 has already been propagated to. So I think this might be another case where we want to stop sending the message out, and that would be or a child computer already has a faster message. There's like a couple reasons we wouldn't want to keep sending the message. And actually all of this, one more thing to note, I'm just gonna like keep a note for myself, is this requires like some global state of which messages have reached. So kind of like what I'm thinking is when we're checking whether we should propagate the 3, we need to know that the 2 is already there.
Yeah.
So, and then in this case, one more thing is if, in this case, if there already is a message there, but it's longer, then we kind of want to override it to replace it, basically. Okay. And at the very end, since we did say that we would keep a global state of like what the shortest message is that has reached these computers. And the answer we're looking for is how long does it take for the message to reach all the computers? So the answer in this case would be 4 seconds because that's the longest it takes. And so at the very end, we want to look at times for each computer and take the longest time, or the maximum, let's say. So yeah, that's kind of how I'm thinking about going about this. Does that sound good? Do you have any questions?
I think this sounds reasonable.
Okay. All right, so maybe we can switch over to coding now.
Sounds good.
All right, so I'm just copying over our pseudocode. Our test case. So I'm going to start with a function. I'm going to do this in Python, by the way.
That's fine.
So I'm going to start with the function. Let's say it's propagation time, and it takes in our edges, and also we can take in like a starting node. And I think we also said, I don't know if this was said directly in the question, but if there is a node that's not connected to anything, that wouldn't be represented in the edges. So we would need to also have like a total number of nodes, just in case one of the nodes is not part of the edges list.
Yeah. That's a good edge case.
Yeah. So because we said this was a graph problem, this edges list is not a very common representation of a graph. And we're going to need to do things like find all of the children for a certain edge, which would be, it would take a lot of time because we'd basically have to go through this entire list.
Yeah.
So I think what I'm going to do, since we're solving this as a graph problem, is just create like a adjacency list for the graph out of these edges.
Sounds good.
So we have each edge, so I'm going to go through. I'll do this with a dictionary. So each key would be the edge, and then the values would be a list of its children, basically.
Okay.
So for each edge, and we can actually kind of, these are tuples. I think in Python you can like deconstruct these in the for loop. So I'll say this is the node, this is the child, and then this is the, say, the time, that basically the edge weight. And for each one, we have a couple cases here actually. If there's nothing in the graph for that node, so for example, if it's not initialized yet, then we would need to initialize it with a list. So I'm going to say, this is if we haven't added any children. So I'm going to say it's a list that includes one child, which is the child and the time. And if we've already added some children, then we want to append to this list. So say, let's test this really quick on our case. Let's see, what's this? Oh, just try printing this out. Okay, so we get 1 is connected to 2 by 2, and 3 for 2 seconds, and 4 for 6 seconds. 2 is connected to 3 by 1 second, and 3 is connected to 4 by 2 seconds. So this looks right. I think one thing that we have to remember to do is, like, if we don't have any of these in here, for if we have more nodes than we have, if the node is not in the edges list, then its children would be an empty list.
Yeah.
So we just have to remember, since it's undefined right now, to like treat it as an empty list when we use it later on. Okay, so we have our graph. And then what did we say we were going to do in our pseudocode? So we said we're going to start with the source node, and it takes 0 seconds to get there. Okay. So actually, can we go back to the
Sure. To the pseudocode?
yeah. So yeah, we said we wanted to start with 0 at the source node because it takes 0 seconds to get there. That's where we're starting. And we also said we want to keep track of the shortest time it's taken to get to each one of these computers.
Yeah.
But before we start doing the propagation or our algorithm, we actually don't really know for these ones what it's going to be yet.
Yeah.
So I'm trying to think of what we can basically, if we want to initialize these so that we can change them, as the messages propagate, we can update it. I know one thing that is pretty common, like in these scenarios, is we have these rules where a message is coming down. Let's say this is like 2. And we already have this rule we've seen in other cases where we want to take the smaller of these 2 values, right? Whichever message kind of got there first. And one way that we could do this is if it hasn't seen a message yet, we can start out by setting these to infinity so that the first message that it sees, it'll always pick that up. It'll always like basically overwrite that. And that'll happen with all the other ones as well. So
Yeah.
I'm thinking we can start out with infinity for the rest of them.
Okay, I think that makes sense. Do you want me to switch back over?
Yeah.
Okay.
Okay, so we'll call this, let's say this is min times, and we'll say that we should have them be infinity for everything except for the starting one, which is 0. So I think this is how you do infinity in Python. And just do basically for every node in this range of nodes. And then we'll say in time of the start node equals 0. Okay. So now we want to propagate messages to the children and take into account the edge weight. So I remember I mentioned recursion back there for like a propagation mechanism. But I think because we have to keep track of this global state of the times for every computer, I think recursion would be a little bit cumbersome because we would it's a little bit strange to share a global state across multiple function calls.
Yeah.
And if we wanted to pass in this global state as a parameter, we could run into some issues as well from it not being updated. So another way we can do recursion, which is pretty similar. So recursion would basically just be saying, okay, I got to this node. Now I want to execute the function for this node eventually. Like at some time, I want this node to do the same thing as all the other nodes are doing, propagating the messages. And we can actually keep track of that ourselves in either a stack or a queue. We could say, like, here is the list of all the messages that I have not yet propagated, and kind of just go through that one by one and propagate them. Does that make sense?
I think so.
Okay. So I'll just I'll just have it start out with a list for now. So I will say this is like messages to propagate. And right now at the beginning, we only have one message, and that's coming from the start node. And we'll just say where the message is at and how long its journey has been so far. So let's look at what else. What do we want to do next? All right, so now we're kind of into the actual propagation part. So we want to kind of continue propagating while there are still messages to propagate. So I'll just write some pseudocode here. We'll come back to this later.
Okay.
But while we can still propagate, we want to take a message and then send it to all the children. So we'll just get a message. In this case, this is going to be getting this 1, 0. So take the first message. I'm actually going to take it out of the list because we don't want to process this message multiple times. And we'll say that this is the node that we were at, and this is our message's current time, just like how long it's been active. And we want to propagate this to each of the children if some of these conditions are true. So let's see, our children are, we have our graph. So the graph at this node value. And we also remember this node is not going to be defined for everything possibly. So we want to say if it's in there, then we want to get the children in the list. But otherwise, we'll just assume that it has no children.
Great.
We'll give it an empty list. So we have the children, and for each of the children, we want to propagate that, and we can do that. We can do another deconstruction here. So the child is, each thing in the list is the child and the time. So child node, and this is the age time. And we said there is a couple conditions on whether we want to propagate it or not. One was if it has children, which we're already kind of accounting for here. If it doesn't, then we're not going to go into this for loop. And the other one was if the child already has a state that is less, it's already been reached by a message in less time. So we can actually check this with our min times, this global state that we're holding. So I actually will say another thing about min times is indexed from 0 to n-1. But really we want it to represent our vertices start from 1 and go to n. So actually we should have actually like we're 1 off on looking at the min time. So like if we want to look at vertex 1, then we want to look at min times at 0. So I'm just going to add these like -1s here. So one. This is our, what is this? This is the fastest so far. we said the fastest so far is, well, if it's less, then we don't want to do anything, actually, because we don't want to propagate it.
Yeah.
So we really only want to propagate it if it's greater. And what is it greater than? Well, we have the message. Let's say right here, this message is going to be 0. But we actually have to add the edge weight to that because we're going to the child. So so we'll call this the incoming time. And that would be the message's current time plus how long it took to get to the child. And so if the fastest so far is greater, that means we want to, well, one, we want to update this min times for the child.
Yep.
To say that a message got there faster. And we'll say that's the incoming time. And then the other thing we want to do is continue to propagate this message. So what we can do is we can just add this message to the our list of messages that we want to propagate. So this is the child, and its lifespan is the new incoming time. So yeah, we can just go through one example. I'll just go through like one iteration of this, but we have the messages to propagate. While we can still propagate, we still need to figure this out. So we have 1, 0. We're starting at the first node. We take the first node, we find its children. For every child, we find basically how the fastest so far, which is in all these child's cases is going to be infinity. And we have the incoming time, which for each one is going to be however much the edge weight was, since this is 0. And so the incoming time should always be less than infinity. So 1 will update each of these children to have the correct new time. And then we'll also propagate all of their messages as well. And so this should continue going. And I think what we want to put here for this while loop, we want to continue going until we don't have any more messages to propagate. So I'm just going to say this is while messages, the length of messages, while there's still messages in there, basically. Yeah, so I'm kind of curious to see what we get here. I think this should work, but let's just return, for now, let's just return the min times to see what we get from this. So propagate time for the edges, our start node is going to be 1, and we have 4 nodes. So let's run that and see what happens. Okay, so this actually looks this looks like exactly what we got in our drawn example. And so this looks right. But we do want to take the maximum of that, because that's what we actually want to return.
Yep.
And so we get 4. But now let's try, I know we had that one other edge case, which was, let's say we have some edges. We'll just increase the number of edges here. So we have one edge or one vertex that is not in the edges list. So it's on an island, basically. We'll see what happens. Okay, so we get infinity. So here we can do, it seems like if an edge is not reached, we'll probably get infinity. So we said we wanted to return -1, so
Yep.
I'll return the new variable for this. And say we'll return the max time. I don't know if you can, I actually don't know if you can do equality with infinity. Well, we'll see if this works.
We could try it.
Okay, cool. So we did get
Nice.
-1. We'll try the other case also. And yeah, we got 4.
Great.
Nice.
Okay. This looks good. Let me add another quick follow-up to this. So what if instead of saying we want to get from one computer to all the others, what if you want to get from one computer to a specific other one in the network?
Mm-hmm. Yeah, so do you want to go back to the
Whimsical?
the whimsical? Yeah, so we want to get from one to a single other computer. Let's say we want to get to this top one up here, from here to here.
Mm-hmm.
And we want to do it in the shortest amount of time possible, right?
Yeah.
Yeah, so we have a direct connection here, and we have some other connections that go off into we don't know where they go off to. If we're just sitting at this one computer, this could eventually get back here.
Mm.
But we're not really sure if it could get back there or not. And we're not sure if it can get back there in like a larger or in a shorter amount of time.
Yeah.
So one thing I'm thinking is, let's say we continue with our like propagation strategy. And this is 2, this is 6. And let's just say, we'll just change this to be 7. So now we're in a situation where we've already gotten, if we're still keeping track of this global list, we've already gotten to the computer in 6.
Mm-hmm.
We know that there's no way that this 7 can propagate anymore and get to 6 unless we had some negative times in here, but I'm assuming we're not going to have any negative times.
No.
Yeah. So I think one way that you could do it, and this is actually like how Dijkstra's algorithm works, is it gives priority to smaller messages, basically.
Mm.
So if we had, say this is our list of messages that we want to propagate, we'll call this like our queue. And so we start out with, it's kind of hard to get an even circle here. Whatever. We start out at the first node, and that's at 0. And then we look at all the children, and we say, okay, we got to the second node in 7 seconds. We got to the third node, and we're still adding all these to the queue. We got to the third node in 2 seconds, and we got to the fourth node in 6 seconds. So like one thing we can do, and then this would be grayed out because we've already processed it. So one thing we could do is we could order these basically by how long they've taken so far. So we could like put the 7 down at the bottom, put this 2 up here, put the 6 here, and so on.
Mm-hmm.
So if we do this, And then we're only taking routes that we know are not longer than other routes that we've already tried, basically. So I think this could like improve performance a little bit. Like obviously the other algorithm still work for a single node because we get the shortest path for every node.
Yeah.
But this could actually improve it a little bit.
Okay. That sounds good. I don't think we need to code this one up, but I thought it was a good thought exercise to go through. Great. All right, this was great, Daniel. Thank you so much. You're a mentor, right, for other people who are looking to practice their software engineering interviewing skills?
Yeah. I'd
Okay.
be happy to mentor other people.
Could you tell us a little more about that? And also what advice you would give them for this kind of question?
Yeah. So yeah, most of the people I've mentored have been students out of college or early in their career. And I think it's definitely involves a lot of practice and looking at questions and trying to fit those questions into like concepts that you already have in your mind. So this problem turned out to be a graph problem. And the only reason I knew it was a graph problem is because I've seen a lot of graph problems and it's very similar. So that's one thing, is to be able to be like solid on different types of problems, kind of like the tools in your toolkit. And then another thing is, I think it's really helpful to, at the beginning, draw out, maybe even on paper, or go through some examples, because that's another way that you can see this is a graph problem. All you have to do is basically just draw out the question verbatim, and you can see here are the nodes, here are the edges. So yeah, don't be afraid to play around with the problem in the beginning and make sure you have the correct abstraction.
Sounds good. And I think a couple of other specific things that I noted during this mock interview, it was really great just how you stopped periodically and ran whatever code you were writing after you had gotten the pseudocode down. I think that's just also really helpful to keep the interviewer on track with what you're doing, and make sure that you are also on track with the right solution, and to debug a lot faster so that they don't really accumulate towards the end and kind of get messy.
Definitely. Yeah, that's a common mistake I see, is you get to the end and one of your helper functions is not working, and it's so hard to find. And then you spend way too much time at the end trying to figure out the issue. So yeah.
So little pieces, and test the small pieces periodically.
Yeah, good advice.
Great. Thank you so much, Daniel, and good luck with your upcoming interviews.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video is valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching, and good luck on your upcoming interview.